Interstellar travel is horrible. What with the cramped quarters of your spaceship and only the thin hull separating you from deathly cold and deadly cosmic rays. Much safer to stay here on Earth with our gloriously habitable biosphere, protective magnetic field, and endless energy from the sun. But what if we could have the best of all worlds? No pun intended. What if we could turn our entire solar system into a spaceship and drive the sun itself around the galaxy? Well, I don't know if we definitely can, but I don't know if we definitely can't. Moving the sun would be a prodigious technological feat, an act befitting a Type II civilization on the Kardashev scale, the same technological realm as building a star-encompassing Dyson sphere. Although it'll be several centuries at least before we can reach that level, the actual physics of a stellar engine is easily explained in a short YouTube video in 2023, and that's what I'm going to do today. It's really just Newton's laws of motion. Newton's first law tells us that objects tend to coast at a constant speed unless acted on by an external force, say, the mutual gravity of the rest of the galaxy holding our sun in its orbit. But it's also possible for an object to change its speed through propulsion, ejecting a smaller part of itself at a very high speed in the opposite direction of the desired motion. Newton's second law says that every action has an equal and opposite reaction. If, say, a rocket blasts its propellant, the act of blasting pushes the rocket forward. This is just the conservation of momentum. A stellar engine follows the exact same principle, with a mild additional technical challenge of building a solar system scale structure to do the job. Although it sounds impossible to move something as massive as the sun, which weighs more than 300,000 Earths, we have a ready-made energy source to do so, the sun itself. It was Fritz Zwicky who first came up with a scheme to move the sun. Zwicky had a lot of wild ideas. He was the first to ponder the possibility of dark matter and predicted the existence of neutron stars and gravitational lensing long before they were discovered. In 1961, he proposed the first stellar engine. It was a giant particle accelerator in space that would shoot pellets at the sun at close to the speed of light. With enough kinetic energy, these would ignite fusion on impact and blast jets of matter off at high speed, pushing the sun. The sun's material would be its own propellant and energy source, although we'd need to come up with at least enough energy to power the particle accelerator. Now, Zwicky never did the math on how much fuel this would take or how fast it would go, and in his classic style, he never returned to this idea. But the proposal inspired humanity, or at least a few of us, to start thinking about how to move the sun. The next serious proposal came over 2 decades later. In the late 80s, Soviet aerospace engineer Leonid Shkadov came up with a concept that doesn't require any external energy source, nor even a propellant. The Shkadov thruster relies on the fact that light itself carries momentum. Each photon carries momentum away and pushes the sun an infinitesimal amount in the opposite direction. The push is very tiny, and photons are emitted evenly in all directions, so the sun stays put. But what if the sun could be coaxed into shining more in one direction? Shkadov's proposal was to build a giant parabolic mirror made of a super-thin foil, the size of a planet's orbit. Photons hitting the mirror would be reflected back, transferring momentum to the mirror in the process. If placed just right, this outward radiation pressure would be perfectly countered by the inward pull of the sun's gravitational field, enabling the mirror to remain in a fixed position relative to the sun. The mirror is a solar sail in the truest sense, powered by sunlight and pulling the sun itself. There are 2 ways to think about how this works. One is that we consider the sun and mirror as a single system that radiates light preferentially in one direction. Conservation of momentum then demands that the system accelerates in the opposite direction. Another way is to think of the mirror as a giant gravitational tugboat. In this interpretation, the sun's radiation does indeed cause the mirror to accelerate in the opposite direction of the incoming photons. But the sail's own gravitational field tugs the sun slightly so that our star accelerates with the sail. Same effect, different interpretations. Positioning the sail determines the direction of motion, which could, in principle, be in any direction. You might want to be careful to keep the sail above or below the planetary orbits, however. Otherwise, you get roasted passing through the reflected beam, or freeze passing through the shadow of the sail.